Hi everyone. Today our group will be presenting on the intermittent renewable energy storage system, covering the challenge of renewable energy availability and the key storage technology that can address them. I'm Chae Kyung Yeon, and now we get us started. As global energy demand continues to rise, there is increasing pressure to reduce carbon emissions. Key renewable like wind, solar, and hydropower offer clean alternatives. However, their output is weather dependent and unpredictable. Fossil fuels, while reliable and adjustable to demand, emit greenhouse gases that contribute to climate change. The core issue is that renewable don't always produce energy when we need it. Solar peaks in summer, but demands peak in winter. This seasonal mismatch between supply and demand is challenge we are addressing. Our current grid infrastructure was not designed to handle renewable availability. As Jim Watson of the UK Energy Center emphasized, there is an urgent need to prepare for energy system change due to growing renewable deployment. Without storage, excess summer energy goes to waste while winter demand goes unmet. The solution lies large-scale storage technology, PSH, batteries, CAES, gravity storage, and hydrogen, which our team will now cover.
Pump storage hydropower is the most established large scale energy storage technology, making up over 90% of global long duration storage. It works by storing excess energy and releasing it when demand is high, which is especially important with renewable energy. Its biggest strength is the ability to deliver large amounts of power over long periods, often more than 10 hours, and respond quickly to grid changes. However, it does require specific geography and has high upfront costs. Overall, it's still one of the most reliable solutions for large scale energy storage. Second, we have the grid scale battery storage. The grid scale battery storage is growing rapidly and is key for integrating renewable energy. Most systems use lithium ion batteries, especially lithium iron phosphate, because they are efficient, safe, and cost effective. Their main advantage is fast response time, making them ideal for short term grid balancing and stability. They are also flexible and can be deployed almost anywhere. Although there are challenges with raw material and cost, battery storage will play a major role in future energy systems.
The next technologies are compressed air and gravity storage. They are mechanical energy storage systems used mainly for long duration applications and grid stability. Compressed air energy storage, or CAES, works by using excess electricity to compress air and store it underground. When energy is needed, the air is released to drive turbines and generates electricity. Gravity storage is a newer approach that uses electricity to lift heavy masses and release them later to generate power through gravitational force. These systems have advantages such as long lifespans and lower costs compared to batteries. This makes them suitable for large scale storage. However, CAES requires specific geological conditions, and both systems are generally less efficient than batteries. Gravity storage is also still in early development. Overall, they are useful for long duration storage but are limited by location and efficiency. The next technology is hydrogen energy storage. It is an emerging solution for large scale and long term energy solutions. It works by using excess electricity to split water into hydrogen and oxygen through electrolysis. The hydrogen is then stored and later converted back into electricity when needed. A key advantage is that hydrogen can store energy for long periods, even weeks or months, making it ideal for seasonal storage. It can also be used in other sectors like transportation and industry. However, it has low efficiency, often below 40%, and requires expensive infrastructure for storage and distribution. Despite these challenges, hydrogen is considered a promising future solution for long-term energy storage.
Now that we looked at each technology individually, let me compare them side by side. As you can see on this table, each technology has different strengths. Pumped storage hydropower has the largest capacity, around 200 gigawatts globally, with 70 to 85% efficiency and 10 to 20 hours of storage. However, it requires specific geography. Grid-scale batteries are the fastest to respond, with up to 95% efficiency. They're ideal for short-term balancing, but they can only store storage energy for 1 to 4 hours. Compressed air storage offers long duration potential at lower cost, but at only 40 to 70% efficiency, and it is limited by geology. Gravity storage is more efficient at around 8%, but it is still in early development. Hydrogen is the only technology that can store energy for weeks or even months, but its round trip efficiency is below 40% today. The key finding is this: no single technology can solve the full challenge. A hybrid approach using multiple technologies together is the most effective solution. To conclude, renewable energy intermittency is the major engineering challenge that requires a multi-technology response. Pumped storage hydro handles long-duration storage. Batteries manage short-term balancing, and hydrogen covers seasonal storage needs. Civil engineering plays a central role in all of this, from designing dams and reservoirs for PSH to building CAES underground caverns to developing hydrogen pipeline infrastructure. With continued innovation, policy support, and investment, this diversified storage portfolio can perform the foundation of a clean and reliable global energy system. And these are our references. And thank you so much.